Last session we have just started on the classification of elements, right? So let us see the first classification. What is the first classification? So let me write it clearly that subject is network theory. And what is the chapter? Chapter is what? DC circuits. And what is the topic? We are in fundamentals, okay? We are in fundamentals of DC circuits. Fundamentals of DC circuits. So we stopped the last session at classification of elements. Now let us quickly look at the first classification is what? Active elements and passive elements. What is an active element? What is the example for active element? Usually people give active element example means voltage source and what else? Current source. Passive element means what? Resistor, inductor, capacitors are called passive elements because people, why they are called voltage source and current source as an active element, when you ask them, they tell that voltage source and current source both will supply the power. So any element which supplies the power is called an active element, usually. Yes or no? And any element which absorbs the power is called a passive element. Usually the people define like this. But if you define like this, there will be a controversy. Sometimes when you face an interview, people may ask you these fundamentals and they expect the proper definition so that there is no controversy. Look at this, all of you. For example, if you define active element as an element which supplies the power and passive element is an element which absorbs the power, you look at this, what is happening here. This is the voltage source and this is a capacitor, this is a resistor here. And now the switch direction is placed here from A to B or moving. Initially, the switch is placed at A for a long time. Initially, the switch is placed at A for a long time. What happens then? The capacitor will get charged to what? Okay, V. And now, in this case, what's happening? The voltage source is supplying, the capacitor is absorbing. Yes or no, all of you? Therefore, according to the definition given by you, an element which supplies the power is called an active element. Therefore, the voltage source is an active element. And now the capacitor is a passive element. Now let us move the switch from A to B. What will happen? The capacitor, because it was charged already, now it starts supplying, okay, it starts supplying power to what? The resistor. The resistor is absorbing, therefore it is a passive element. But the capacitor is now supplying the power. Can we call it as an active element? No. Any element which supplies the power is called an active element. If you define like that, definitely there could be a controversy. You take charged inductor, charged capacitor may also supply the power. Does it mean they are active elements? No, definitely not. But how do you define it? If you observe carefully here, when you keep the switch at A for a long time, the voltage source is supplying the power to the capacitor. And the voltage source will supply the power to the capacitor. How long? It can supply the power to the capacitor for infinite time. Continuously for infinite time. Provided it's an ideal element. Again, that is also one important point we need to note down. If capacitor now it is supplying the power in the second case when the switch is moved from A to B because it was already charged, the capacitor is supplying the power, but how long it is supplying the power? It supplies only for some time, not for infinite time, like a voltage source. Yes or no, all of you? Therefore, you need to define the active element is the one it supplies. It's a very, very important definition. It supplies finite power. Write down, all of you, for infinite time. All of you please write down quickly. It supplies finite power for infinite time. But do you have any element which can supply finite power for infinite time in reality? Practically it is not possible. Only ideally speaking it is possible. That is why the example for active element, it is not simply voltage source, it is ideal voltage source and ideal current source. These are the examples. You cannot simply say the voltage source or current source. Again, a controversy may arise. Ideal voltage source, ideal current source are the elements which can supply finite amount of power continuously for infinite time. Understand all of you? What about passive element? It either absorbs power. It either absorbs power. Okay? Because we know that any passive element will absorb the power. But it also supplies the power. If we have a charged capacitor, it's supplying power. If you have a charged inductor, it is also supplying the power. Therefore, it either absorbs power or supplies finite power only for finite time. Please note down all of you. Okay, I think all of you got a clear idea. Please note down quickly. Also note down this particular figure so that okay, you can easily remember the definitions. Why we are defining like this, you can easily understand by looking at this particular figure. Quickly note down. Now, there are some special cases. Transistor, op amp, or any amplifier, note down, or any amplifier can be treated as active elements. Understand all of you? Okay? So this is a special case. There is no relation between this particular case and the definitions given over here. Understand all of you? Okay? So therefore, you can write down transistor, op amp, or any amplifier can be treated as active element. So based on this point, we generally divide the filters into two categories. What are they? Active filter and passive filter. Active filter and passive filter. You understand? What is an active filter? It consists of resistor, capacitor, either op amp or any amplifier or any transistor. Okay? You may have anything over there. The inductor is absent in this particular case, active element. Active filters. Active filters do not contain any inductor because inductor is a bulky element, heavy element, and is also very expensive. Okay, so that is why inductor is avoided. Inductor is usually avoided. L is usually avoided. All of you can note down. Usually avoided. Inductor is usually avoided. Due to its high cost and bulky size. What about passive filter? It consists of what? Resistor, inductor, or capacitor, or combination of all these. If you want first order filter, RC or RL. If you want second order filter, L and C are must. At least one inductor, at least one capacitor must be there for higher order filters. Yes or no, all of you? But how do you achieve the higher order filters in case of active filters? You can achieve higher order filters here. Okay, the first order filter will have either RC or RL. But second order filter will have, okay, L and C compulsory, or depends on your requirement, but L and C are compulsory. Okay, so this is what the first order and second order filters contain. But how do you achieve the higher order filters? Using R, C and op amp. We avoided here the inductor because it's bulky. Yes or no, all of you, and also high cost. But we are preferring here inductor. It is only to what? To achieve the higher order filters. Because though you have a facility RC and RL, but usually we do not prefer RL because L is expensive. L is bulky in size. Okay, but in higher order filters it is unavoidable. Without inductor, using just a capacitor, you cannot achieve the higher order filters or second order filters. Understand, all of you? But you can achieve the higher order filters. The operational amplifier will help you because op amp can be used as an integrator, okay, can be used as a differentiator. Yes or no, all of you? It can be used as an integrator or a differentiator or simply an amplifier, or it can be simply as a buffer. So many things you can do. Okay, so if you have these two op amps in cascade, what will happen? Tell me, all of you. What will happen if you have two op amps in cascade and one op amp is acting as what here the integrator, the second one is also integrator. Together it is acting like what? 1 by S square. Therefore, you can achieve these higher order filters using operational amplifier. Understood, all of you? Okay, so don't worry about that. The op amp can be taking care of that higher order case. But here, just using capacitor cannot do. That is why in higher order case we go for what? RLC or simply LC combination. So please note down, and also please write down here. L is usually avoided in case of what? In the construction of active filters due to its high cost and bulky size. Note down. Okay, hope you have written that. Now let us look at second classification. Linear element, non-linear element. Linear element and non-linear element. What is a linear element? An element which obeys, yes or no? An element which obeys Ohm's law. What is a non-linear element? An element which does not obey Ohm's law. An element which does not obey Ohm's law. An element which obeys Ohm's law is called linear element. An element which does not obey Ohm's law is called non-linear element. Then what are the examples for linear elements here? R, L, C elements. What are the examples for non-linear elements? Diode, transistor, okay, and all semiconductor devices. Otherwise you can write that, okay, you can write that, all semiconductor devices. All semiconductor devices are called non-linear. Okay, all semiconductor devices are called non-linear elements. Okay, but does it mean that all non-linear elements are semiconductor? No, there are certain elements which are not semiconductor, but they are non-linear, which we use in our day-to-day life. Very frequently we use certain elements, okay, which are not semiconductor, but they are non-linear. Can you really identify those elements? Do you have any idea what are the elements which are not semiconductor but non-linear? You might have come across thermostat applications, where you generally use these thermostat applications in temperature control, automatic temperature control. Okay, you heard about thermistor, I think. What is a thermistor? Thermistor is used in iron box. Thermistor is used in geysers, water heaters, air conditioners. So many. Air conditions, and you have heaters, geysers, and iron box, which we use in our day-to-day application. Wherever you have a temperature control, usually these thermostat applications will come into picture. Thermistor is one important element. What is a thermistor? It is basically a non-linear resistive element. Understand, all of you? There is one more element which we use in our day-to-day life, okay, without which we cannot imagine the protection of this entire electric system. Okay, what is that element actually? You heard about fuse. What is a fuse actually here? A fuse is a non-linear resistive component. You understand? Fuse is what actually here? A non-linear resistive component. A fuse is the most sincere, honest, and reliable element. Why it is called sincere, honest, and reliable element? To protect the entire system, or in protecting the entire system, this fuse is called most reliable and honest element. Why can't we take other elements which protect the system? Nowadays people are using circuit breakers. What is a circuit breaker? Mini circuit breakers people call it. In domestic applications, people use mini circuit breakers. What is a mini circuit breaker? MCB you call it in a short form. It is just a mechanical switch. When high current is passing through that particular switch or in a particular path, then it will automatically get tripped. Okay, that facility is not there in the fuse. But in case of circuit breaker, if any malfunction occurs, and when high current is passing through it, because of malfunctioning, after all it is a mechanical switch, if it doesn't respond or if it doesn't function properly, then what will happen? Then it passes what? Or it allows what? High current. Then obviously it may damage the devices like your fan or tube or bulb or any computer, any other major device or important device in your domestic cases maybe get damaged. But fuse is not like that. Fuse actually, it just burns itself. It never let others burn. It just burns itself. That's it. So fuse is the most honest element and reliable element, which is very important element. That is why in most of the critical applications, though we got a good technology, okay, most of the critical applications, people use the fuse instead of circuit breaker. Most of the critical applications. Okay, so write down please all of you. Note. Why this note? Tell me. Because we have given a conclusion that all semiconductor devices are nonlinear. But all non-linear may not be semiconductor. Understand? Okay, for that, note down here. Thermistor and fuse are non-linear. Thermistor and fuse are non-linear resistive components or resistive elements. Thermistor and fuse are non-linear resistive elements as they do not obey Ohm's law. As they do not obey Ohm's law. Thermistor and fuse are non-linear resistive elements as they do not obey Ohm's law. Okay? Now, let us look at the first one, resistor. V and I. We know that I is directly proportional to V at a constant temperature. Is equal to V by R or G into V. This is Ohm's law. Okay. And if you draw the characteristics, Vi, a line passing through the origin, of course it passes even in the other quadrant. Okay. A line passing through the origin both in first quadrant as well as third quadrant. We also know that this R is a passive element. Just now, a little while ago, we have studied examples for passive elements are what? RLC elements are passive elements. Yes or no? Therefore, look at this. Now, you have a passive element which has the characteristics in what? First and third quadrants. Understand, all of you? Remember, it's a very important point to note down that every passive element will have the characteristics in both first quadrant as well as what? Third quadrant. So please note. Again, put a note and write down. First you note on that and then put a note and write down. And you see here the slope G or 1 by R. G or 1 by R. And put a note and write down here. Every passive element, after writing this, every passive element will have characteristics in both first and third quadrants. Every passive element will have characteristics in both first and third quadrants. Every passive element will have characteristics in both first and third quadrants. Because sometimes in the exam, you may get the question that, which of the following characteristics will refer to a passive element. So what do you identify? Which of the characteristics are having in both first and third quadrant, okay, you have to choose that particular option. He may give you 1, 2, 1, 3, 1, 4 or only 1. I mean first quadrant, first and second quadrant, first and third quadrant, okay, or first and fourth quadrant. You have to choose just obviously first and third quadrant. Okay. So I think all of you understand this. Now second one is what? Inductor. So inductor. So when some current is passing through it, then obviously it produces a flux, and that flux is linking with the coil, and the flux linking with the coil is directly proportional to the current flowing through it. And again, you can remove that proportionality, L into I. Okay, phi is equal to L into I. It is also something like Y is equal to mx, just like I is equal to V by R or I is equal to G into V. It is also Ohm's law. It is also Ohm's law, no doubt. It is another form of Ohm's law. Ohm's law is for inductor, Ohm's law for capacitor, Ohm's law for resistor. You can define. And if you differentiate on both sides, so what do you get here? d phi by dt. What is d phi by dt actually here? d phi by dt is equal to L into di by dt. This is nothing but d phi by dt. Time rate of change of flux is nothing but EMF. EMF is nothing but what? Actually the voltage. So voltage V of t is equal to L into di of t by dt. So this is also Ohm's law. Understand? This is also Ohm's law. Now, let us look at the current. How do you find the current here knowing the voltage? I of t is equal to 1 by L integral. You are supposed to even maintain the limits. Most of the people ignore that, but it should be a common practice. When you write current in terms of voltage, the limits must be mentioned. Minus infinity to t, that is V of t dt. Okay? But I can write it as 1 by L I can split the integration minus infinity to t naught v of t dt, okay, 1 by L, again t naught to t v of t dt. Hope you understand, all of you. Okay. Now this particular part, when you see here, this particular part is what? I can write it as what? I of t naught. Why? Because when you have minus infinity to t v of t dt 1 by L is giving I of t. But when you have minus infinity to t naught v of t dt 1 by L, the entire quantity can be taken as what? I of t naught. If it is t naught, it will become I of t naught. If it is t, it will become I of t. That's it. That's it. So I can write it as I of t naught plus 1 by L integral t naught to t v of t dt. What is this I of t naught? Is the initial current. What is this? Initial current through the inductor. What is the initial current? Okay. Now look at this. V is equal to L di by dt can be written as L into the first derivative part can be always taken as the slope of I of t. Now in this case you can write it as I of t naught, that is initial current, plus 1 by L integral t naught to t v of t dt. Integration over the boundaries, first integration, can be taken as what? Area under the curve. Area under v of t. That is 1 by L, that is 1 by L, area under v of t over the boundaries t naught to t. I think all of you understand this, okay? So this is all the Ohm's law only. The first we started here, and then we gone for the differentiation, then gone for the integration, and finally we got all these things. This is all the Ohm's law only in different form for the inductor, you can see. Okay, so please quickly note down, and then we can go for the characteristics of that. First, you note down this quickly. Coming to now the characteristics. Now look at this characteristics. So taking current on y-axis and flux on x-axis. It's again a line passing through the origin. That means when you double the current, then flux will also be doubled. But it does not mean that if you take infinite current, you will get infinite flux. Always there is a magnetic saturation. Even though you increase certain amount of current, or current after certain amount of value or certain particular value here, then the flux will remain constant, or it may not increase in proportion to the current. Okay. After a certain point, the flux remains same. Okay. This particular current you call it. This is called magnetic saturation. You call it magnetic saturation. You call it magnetic saturation. But the same characteristics you can expect even in third quadrant. For a negative current, you get a negative flux, obviously. Yes or no? Then you have again the saturation even in the negative direction. That is a negative current. Okay. Look at this, all of you. One important observation. If you neglect the saturation, you see all linear characteristics. And the slope can also be calculated here. Okay, that is L, nothing but phi by I. Yes or no? But if you include this particular magnetic saturation in the characteristics, the whole characteristics are looking like nonlinear only. Okay? What is an inductor is a linear element, we can say, but does not mean that there is no nonlinear element. Yes, there is nonlinear inductor also. If you neglect that saturation, then you can call that inductor as a linear inductor. If you include that saturation, then inductor might be nonlinear also. Understand all of you? Okay? So based on this, you can divide these inductors into two categories. Inductors of two types. One is a linear inductor. The other is a nonlinear inductor. Linear inductor and nonlinear inductor. What is a linear inductor? You can see in this particular region, if current is doubled, then flux is doubled. If current is tripled, then the flux is tripled. If current is doubled, then flux is doubled, then L value remains same. That means even though the current is doubled, the L value remains same. That means L value is not depending on the value of phi. L value is completely independent of phi. So an inductor is called linear if its L value is independent of its current. Example for linear inductor. Okay, you have a best example, air core inductor. Air core inductor. What about the nonlinear inductor? What about the nonlinear inductor? Look at this saturation. In this saturation, if current is doubled, the flux is remains same. The flux is not getting doubled. Then L value is changing with respect to the current value. When I is changing, L is changing. That means L is depending on the value of I. So L is dependent on I. Understand? If L is independent of its current, then it is called linear inductor. If L is dependent on I, it is a nonlinear inductor. And for nonlinear inductor, you have best example, iron core inductor. Iron core inductor. Understand all of you, okay? So note down these characteristics and this one also quickly. Note down them. Let me take this particular one off. You can note down this quickly. Okay, hope you have written this. Now let's go with the third characteristics here. Okay, third element here, capacitor. If you give some voltage, some charge is deposited on each conducting plate, and the charge deposited on each conducting plate is directly proportional to voltage. Removing this proportionality, then you get CV. This is also Ohm's law, Y is equal to mx. Okay, this is also another form of Ohm's law. For a capacitor, you have Ohm's law. Now, differentiating both sides. dq by dt is equal to C dV by dt. Nothing but time rate of change of charge is nothing but current. First derivative of that particular function can be called slope. All of you please write down along with me because already we have seen inductor, right? So you can write it. Don't waste time. You can write it. Slope of V of t. Okay? When I tell you to write, you can start writing. It doesn't matter, okay? Now, just now we have seen, all of you, when you take the integration, in the case of inductor, V is equal to L dI by dt, then I you have written, what is that? What is that you have written? 1 by C now here, integral minus infinity to t, okay? What is that? I of t dt. Now final conclusion I'm writing here, because I've just split the integration in two parts, minus infinity to t naught, then t naught to t. Yes or no? So final conclusion is what actually here. You can write it as v of t is equal to v of t naught plus 1 by c integral t naught to t I of t dt. You can see here, this is nothing but initial voltage. What is it? Initial voltage. Now you can say the initial voltage plus 1 by c, the area under I of t over the boundaries t naught to t. This is what actually you can write. And the characteristics, if you see, voltage on x-axis, charge on y-axis, okay? It's a line passing through the origin, but the same thing may happen even in the third quadrant, yes or no? Even in the third quadrant, the same thing will happen, okay? Linear, okay? It's not non-linear, it's linear. So you can take now this one as but you also have, what is that? Saturation. You cannot get infinite charge by taking infinite voltage. And for both positive and negative values of the voltage, you can have the characteristics. Why you got this one here? Because of electric field saturation. Magnetic field saturation, electric field saturation. You cannot store infinite amount of energy, okay, in the capacitor. You cannot store infinite amount of flux or infinite amount of energy in the case of inductor. Okay? And neglecting this particular saturation, the slope, if you calculate, what do you get? It is C, nothing but Q by V. Understand all of you? Okay. Again, if the capacitor electric field saturation is taken into account, the capacitor will become non-linear. Understand? Okay. So when you are answering the question that what is the linear element and what are the examples for the linear element, you can tell that RLC elements are linear elements, no doubt. But still, if you go a little deeper, you have nonlinear resistors, nonlinear inductors, nonlinear capacitors. Yes or no? Just now we have seen based on the characteristics. Okay? Nonlinear inductor, nonlinear capacitor. Linear inductor, linear capacitor. No doubt in that. Okay? Note down quickly. Note down quickly. For capacitor. The first 10 hours I go a bit slow so that any student can easily follow. The first 10 hours or 10 to 12 videos, let us say otherwise. The first 10, 12 sessions are going a bit slow because most of the people are facing the problems in the fundamentals. That is why I try to stress upon more on fundamentals first. Then later it is easy for me to take you at a faster rate. Okay? Hope you have written. Third classification, unilateral and bilateral. Unilateral element and bilateral element. Okay? What is a unilateral element? Example, diode. Yes or no? What is a bilateral element? resistor, inductor, and capacitor. These three are bilateral elements. RLC elements are bilateral elements. Yes or no? But diode, transistor, thyristor, you take any semiconductor, okay, they're all unilateral elements. What's the reason for that? Most of the people define that, unilateral element is an element which allows the flow of current only in one direction. If that is the case, what is it basically? Is it a unilateral element or bilateral element? Yes. Is it a unilateral element or bilateral element? The flow of current is available in both the directions here. Yes or no? But does it mean it's a bilateral element? No. People define that the bilateral element is the one which allows the flow of current in both the directions. Unilateral element is an element which allows the flow of current only in one direction. Do not define like that. Maybe it is an ideal case, it might be true, but sometimes you maybe ask the question that, which of the following characteristics will refer to unilateral element? Okay? Or he will give you a characteristics and he will ask you to describe whether it's unilateral or passive or active, non-linear or linear, like that. Anything might be asked. Remember, the definition must be very clear. According to the definition that any element which allows the flow of current only in one direction, it looks like bilateral, but actually it is what? Unilateral. What is the difference between the bilateral and unilateral? Diode, why it is unilateral? Because it has got two properties. The first property is that forward bias resistance. The second property is that reverse bias resistance. Forward bias resistance, reverse bias resistance. Forward bias resistance and reverse bias resistance. Two properties are there. But you have only one property with respect to the current reversal also. Even if the current is reversed, the property of this element is not changed. L remains same, C remains same, R remains same, even though you reverse the current flowing through it. But if you reverse the current through the diode, the property is not same. You see the property in both the directions of the current, it looks same. The property is same, you can see. But the property is not same here. It is something like this and something else you are getting here. That is why, how you define now a unilateral element. What is a unilateral element? Its property does change, please write down, its property does change with the reversal of current through it. With the reversal of current through it. What about this one? Its property does not change with the reversal of current through it. Its property does not change with the reversal of current through it. This is how you are supposed to define. And the example for unilateral element, all semiconductor. Example for bilateral RLC element. Now you can easily identify what is the unilateral element, what is the bilateral element. Yes sir? Okay. So you can please note down quickly here. Please note down quickly. Unilateral element, its property does change with the reversal of current through it. Bilateral element, its property does not change with the reversal of current through it. Let me highlight does and does not. The property does not change with the reversal of current through it. Okay? This is how you can define unilateral element and bilateral element. And I stop it here. Okay? In the next session, we will see when the characteristics are given, how we identify, okay, whether the characteristics are linear or nonlinear, unilateral or bilateral, active or passive, like that. Okay? So I stop the session here.